Okay, so one of the big ways that functions are identified in the BC exam is using what are called vector valued functions. I will call these VVFs. Okay, so first off we have to know what a vector is. A vector is a mathematical entity that oftentimes is pictured as an arrow that has two important quantities. It has a distance and it has a direction. So distance and a direction. If it has these two things, we can view this as a vector. Sometimes the distance is referred to as a magnitude. So those words are somewhat interchangeable when it comes to vectors. So if I have a point A and a point B and I have a vector that connects them, right? So the initial point of the vector is A, the terminating point of the vector is B. We can call this vector, let's call it vector V. Vector V is a displacement vector. So the idea here is as if I was to move from A to B, the movement from one point to the other would describe the displacement. Okay? It's not necessarily the path that I traveled along, but given the starting point and the end point, it describes how far and in what direction I have been displaced. Okay, in order to have a vector algebra, I have to have a couple of things understood. So I have to have the idea of equivalent vectors. So when are two vectors equal? So let's say U and V are vectors. That one's a V, are vectors. And they are in such a way that they head in the same direction and they have the same magnitude. So they both have the same direction and the magnitude of U is equal to the magnitude of V. Then we say that the vectors are equal. So if they have the same direction and the same magnitude, then the vectors are equal. Well, one thing that should be noted is that they are not in the same space. V and U start at very different places. They just go in the same direction for the same distance. Then they're equivalent vectors. Now, we also have to note something else that exists, because it's a bit of a mathematical fiction, is that we do allow for a zero vector, and we define the zero vector such that the magnitude of the zero vector is 0. So this creates an interesting situation. Can you draw a zero vector? Nope. It's just like a little single spot, right? It doesn't go anywhere. So this is important. The zero vector has no direction. It has no direction. It has a magnitude. Its magnitude is 0. And any vector whose magnitude is 0 is equal or is the zero vector. But none of these vectors that have a magnitude of 0 are having a direction. Okay, so being able to describe a vector like saying, hey, it went that way is not really useful. So we come up with this idea of rectangular coordinates, sometimes called Cartesian coordinates. Thank you, Descartes. Okay, so the idea here is if I want to know a way to describe this vector, what I do is I move it. So remember, vectors are irrelevant of their location, and I move it onto the grid. And I put the initial point of the vector here, and then I look at what is the terminal point. Right, so let's call that point B. Right? That's an ugly B. Let's make a better B. There we go. So we use that as its terminal point. So we can describe this vector using the location of its terminal point. So let's say this vector has a terminal point 4, 3. Then I can describe vector v as being the vector for 3. And note, once I have locked in those two coordinates, I know what direction the vector is going in, and I know by the Pythagorean theorem that its magnitude is 5. Right? So the magnitude, that's not the magnitude of 5, the magnitude of v in this case would be 5. So I've locked in both the direction and its magnitude. So this is an adequate and full way to define a particular vector. Okay, so any vector that does in fact start at the origin is what is called a position vector. So it's a vector that's pointing at a particular position. So if I have a vector v and it's a position vector, and I know that it is the vector, let's say 5, 4, then it's pointing at B, then I know that B is the point 5, 4. So a position vector is a vector that starts at the origin and tells the particular position of a point by giving a direction and a magnitude. Since we have a coordinate system, let's say I have a point A at 1, 1, and I have a point B at 4, 3, right? So A is at 1, 1, and B is at 4, 3. Then I want the displacement vector from A to B. So let's let R be that displacement vector, the displacement vector from A to B. Well, then this is going to be 4 minus 1. The x-coordinates subtracted, 3 minus 1. So the displacement vector here could be the vector 3, 2. Okay, so how do we get a displacement vector? It's like x sub 2 minus x sub 1 is the x-coordinate, y sub 2 minus y sub 1 is the y-coordinate. Okay, so that seems to make sense. Okay, we also have a way to calculate magnitude if we have a coordinate system. So if I have a vector v, which is, let's say v is given by x, y, right? So what would its magnitude be? Well, that's the change in x is x, the change in y is y, so the length of that, let's see, the magnitude of v would be then the square root of x squared plus y squared, says the Pythagorean theorem. So there's my definition of magnitude. We have a way to define vector addition. So vector addition, let's say that v is v1, v2, and u is the vector u1, u2, then v plus u is just done component-wise. It's v1 plus u1, v2 plus u2. What's actually happening here is if v goes in that direction for that magnitude, and u goes in this direction with this magnitude, and you put them tip to toe, kind of like that, this vector coming across the center here, the one that would start at the beginning of v and end at the end of u, this one is actually that vector v plus u. So that's the geometry of the arithmetic that you just did there. We also have an idea of what's called scalar multiplication. Okay, so if c is a real number and v equals x, y is a vector in the second space, then c times v is the same as multiplying each component of the v vector by c. Now, what's notable here is that the magnitude of cv is equal to c times the magnitude of v. So what we're doing here is we're creating a new vector. So let's say this is v, and we're going to create a new vector that's in the same direction, but we'll change its and scale its magnitude. So this entire vector would be 3 times v. Its direction doesn't change, but its magnitude multiplies by 3. So this is what we call scalar multiplication. Okay, in the two-dimensional world, we have two vectors that are kind of important. They are called standard basis vectors. And we give them particular letters. We call one I, and we call the other one j. The I vector is just the vector 1, 0. The j vector is just 0, 1. So note, they both have, they're perpendicular to each other. They both have a magnitude of 1. They form kind of like the beginning of the coordinate plane. Note, any vector can be written as a linear combination of these two vectors. So like, let's say I have the vectors 3, 4. I can rewrite that as 3 times I plus 4 times j. You will see this format used to write the vector. I tend to lean toward this type. However, oftentimes physicists and some other folks may use this standard basis format because they're more comfortable with it with their calculations. Okay, so finally, what is a vector valued function? Okay, so a vector valued function is a function that, so if I have a function f, it eats, well, it's going to be f, there you go. It eats a real number and it spits out a vector. Okay, so for example, if I have r of t is equal to f of t, g of t. Okay, so this is like kind of combining the idea of vectors and parametric equations. F of t and g of t would be like two parametric equations. X is the f of t, y is the g of t, but now we're putting it into a vector. So given t, I now know how to find the first coordinate with this rule f and the second coordinate with this rule g. So I might say like r of t is 3t minus 2 t squared, right? So in this case, r of 1 would be 3 times 1, which is 3 minus 2 is 1, and then 1 squared is 1. So this is going to return a vector 1, 1. If I had r of 0, this would have returned the vector negative 2, 0. So every value that you put in for t, put in a value for t, it's going to return a two-dimensional vector as a result. So that's what vector valued functions are. Okay, so let's recap here. We have learned what a vector is. And a vector is something with a distance and a magnitude, or sorry, a distance slash magnitude and a direction. Right? So it has a distance, or sometimes we call that a magnitude, and a direction. A displacement vector just says, hey, it's a vector that tells how I move from one point to another. Right? We have coordinate representation. So I can have a vector 3, 4, which means go to the right 3 and up 4. I have an idea of equal vectors. Right? So they have the same distance and direction. So if two vectors have the same distance and direction, they are equivalent. We have a zero vector, right? And the zero vector is one where the magnitude of the zero vector is 0. we have position vectors, right? So in the position vector, I have the coordinate plane, right? And the position vector tells me where a particular point is. So the vector v here would describe a particular position. So it would be like the point v1, v2, right? So if v is the vector v1, v2, this position is v1, v2. So that's how we figure out a position vector. From there, we got a couple of algebraic tools. We know the magnitude is, so if I want the magnitude of v, right, this is going to be the square root of its components squared, right? If I have addition, v plus u is one component from v plus a component from u, and then the second component from v plus the second component from u, right? Scalar multiplication is a constant times the vector, which is just the constant times its components. We have the standard basis vectors, which is I being 1, 0. J being the vector 0, 1. And then finally we got into vector valued functions, which is that you take some vector at time t, or the vector at time t will be described as some function of t for the x and some other function of t for the y component of the vector. Alright, so there's a quick summary of everything that's in this section. I know it's a long set of notes for today, but there you have it.